Welcome, first-year chemistry students. I am absolutely thrilled to have you here today. So jump in the time machine with me for a second, because in this explainer, we're taking a chronological journey all the way back to the year 1817. Now, I want you to imagine walking into a kitchen to cook this massive, elaborate feast, but the pantry is just a complete disaster. I mean, ingredients are thrown everywhere, you've got flour sitting next to the hot sauce, sugars mixed in with the dried pasta, and literally nothing makes sense. Well, that chaotic, totally unorganized kitchen pantry, that was exactly the state of early chemistry. Scientists were discovering all these incredible new elements, but they had absolutely no system for organizing them. It was a total mess. But today, we're going to look at the very first serious attempt to clean up that pantry.
Okay, let's dive into this. Think of our agenda today as our master recipe card. We'll start in that messy 1817 kitchen, uncover the magic of triads, explore a few more elemental families, see what happens when the recipe completely fails, test your knowledge, and finally, look at how all this inspired the modern periodic table. All right, so let's start by getting our hands dirty and organizing this 1817 chemistry pantry.
I want you to meet our master chef for today, Johann Wolfgang Dobereiner. He was this brilliant German chemist who basically looked at the wildly disorganized mess of known elements and just decided, enough is enough. Think of Dobereiner as a chef trying to make sense of his ingredients. He didn't just want to line things up randomly on a shelf. He actually wanted to group his ingredients by their chemical properties, like how they actually behave, and their atomic weights, which is essentially how heavy they are. As he was sorting through all these elemental ingredients, he noticed something super fascinating. He found that certain elements naturally group together in little sets of 3. He called these sets triads. Within these triads, the 3 elements shared very similar chemical properties. To go back to our kitchen analogy, it was kind of like finding 3 different types of flour that all bake exactly the same way. But, and here's the kicker, it wasn't just about how they acted, they were actually linked by a very specific underlying weight recipe. And here is the exact recipe he figured out. The rule of triads states that the atomic mass of the middle element is approximately the arithmetic mean of the other 2. This was Dobereiner's massive light bulb eureka moment. He realized that if you took the lightest ingredient in the group and the heaviest ingredient and averaged their weights together, you got the exact weight of the middle ingredient. Now, we totally take this for granted today, but you have to understand just how revolutionary this was back in 1817. For the very first time, someone had found a real mathematical symmetry linking how an element behaves to its actual physical mass. It was a game changer. Let's actually put this to the test and look at the magic of the alkali metal recipe. Now, what's really interesting about this is seeing if this mathematical recipe actually works in practice. Let's step up to the cutting board and test it out using our first case study, a family of highly reactive ingredients known as the alkali metals. Let's literally walk through the calculation together step by step. Step 1. We take the atomic mass of the lightest element in our triad, which is lithium, sitting at 6.9. Step 2. We add the mass of the heaviest element in the group, potassium, which is 39.1. So if we add 6.9 and 39.1, that gives us exactly 46. Step 3. We divide that sum by 2 to find the average. 46 divided by 2 gives us 23.0. And guess what the atomic mass of the middle element, sodium, is? Yep, it is exactly 23.0. The average mass of lithium and potassium perfectly matches the mass of sodium. The recipe works flawlessly. No way, right?
Of course, once you find one recipe that works, you look for more. Let's explore some more elemental spices and salts.
Once Dobereiner realized his recipe worked perfectly for the alkali metals, he was hooked. He started looking for other flavor profiles in his chemistry kitchen, just desperately seeking more groups of 3 that fit this incredible mathematical pattern. And he actually found them. Consider the halogen triad: chlorine, bromine, and iodine. You probably recognize some of these from around your own house, right? Chlorine is used in bleach in swimming pools. Iodine is often used as a medical antiseptic. They're basically like different types of harsh salts or cleaning agents you'd keep under the kitchen sink. And just like those alkali metals, they share similar chemical properties, and their atomic masses follow the exact same triad average rule. Chlorine is the lightest, iodine is the heaviest, and bromine sits right there in the mathematical middle. Let's see how this builds with a couple more families Dobereiner successfully grouped. He identified the alkaline earth metals, calcium, strontium, and barium. Again, think of household items. Calcium is what makes chalk, and obviously what builds our bones. He also grouped the chalcogens, sulfur, selenium, and tellurium.
By clustering these matching, sort of household ingredients together, he was slowly bringing order to the chaos. He was proving that his mathematical rule wasn't just some one-off coincidence. It was a real pattern. But what happens when the recipe doesn't quite work out? Let's talk about the messy leftovers.
Now, as beautiful as this symmetry was, we gotta be honest here. Science is rarely perfect on the first try. We have to shift our tone just a bit to address the limitations, because Dobereiner quickly ran into a pretty major problem. Not every ingredient in the kitchen fit perfectly into his triad recipe. I mean, imagine you're cooking, and you've used up your flour, your sugar, and your salt perfectly. But then you look over on the counter and you still have, I don't know, a random pineapple, some beef jerky, and a jar of mustard. Most of the known elements at the time simply did not fit into the triads. They were exactly like leftover ingredients that just didn't belong to any specific recipe. You can totally imagine the intense frustration of early chemists when they realized that while this triad system was super neat, its scope was actually really limited.
So, the crucial point is that while this idea was completely revolutionary, it lacked ultimate scientific rigor for a few key reasons. First, the limited scope. Dobereiner could really only identify a small handful of triads. Second, inaccuracy. Outside of a few perfect examples, like those alkali metals we did the math for, the average mass rule was often just a rough approximation. And let's be real, in chemistry, close enough doesn't always cut it. And third, new elements. As scientists discovered more and more elements, essentially adding entirely new ingredients to the pantry, the rigid group of three system completely fell apart. It just couldn't accommodate the massive diversity of the expanding elemental world. All right, it's time to test your triad knowledge with a quick mid-explainer quiz. Okay, I'm breaking the fourth wall here. We've covered a lot of ground, and as first-year chemistry students, I want to make sure these core concepts are really sticking with you. So let's do a quick, active learning pop quiz. I'll ask a question, give you a second to think, and then we'll reveal the answer together. Question 1. What is the exact mathematical relationship between the atomic masses of the elements in a triad? Think back to Dobereiner's rule. Got it in your head? The atomic mass of the middle element is the arithmetic mean, or the average, of the other two outer elements. Moving right along to question 2. If lithium and potassium are the outer elements of the alkali metal triad, what is the middle element? I'll give you a beat. The answer is sodium. Remember that perfect calculation we walked through earlier. 6.9 plus 39.1 divided by 2 equals 23.0, the exact mass of sodium. Boom. And for our final quiz question, give me just one reason why Dobereiner's triad system eventually became obsolete. Think about those messy leftover ingredients. The main reason is that it just couldn't accommodate the massive diversity of new elements being discovered. The scope was way too limited, and honestly, the math was sometimes too inaccurate to apply to everything in that ever-growing chemistry pantry. Huge congrats if you got those right. Let's move into our final chapter, how these triads inspired the periodic table. We are entering the final stretch of our chronological story today. Now, it's really easy to look at the failures of the triad system and just dismiss it entirely. But in science, failures are literally just essential stepping stones. Dobereiner was passing the torch to the next generation of chemists. But before we look at that grand legacy, I want to leave you with this quick study guide. As chemistry students, you are definitely going to need to have these locked into your memory. We've got our alkali metals, lithium, sodium, potassium, the alkaline earth metals, calcium, strontium, barium, our halogens, chlorine, bromine, iodine, and the chalcogens, sulfur, selenium, tellurium. Go ahead and take a mental snapshot of this for your revision later. And this brilliantly illustrates the entire evolution of early chemistry. Think about Dobereiner's triads, a rigid three-element system with a pretty limited scope, but look at what it inspired. Despite its flaws, Dobereiner's work was the very first to ever suggest that atomic mass is a fundamental property directly related to chemical behavior. It completely shifted the focus of chemistry from just blindly listing random ingredients to actively looking for deeper patterns. That exact mindset paved the way for John Newland's law of octaves and eventually the comprehensive, beautifully accommodating periodic table created by Dmitri Mendeleev, the exact one that you probably see hanging in your classroom today. Which brings us to the very end of our explainer, and I want to leave you with a provocative thought. Dobereiner looked at a chaotic, completely disorganized 1817 chemistry pantry and somehow managed to find hidden mathematical symmetry that fundamentally changed science forever. So as you continue your own chemistry journey, I want you to ask yourself, what invisible patterns are hiding in plain sight today, just waiting for the next Dobereiner to find them? Keep looking, keep questioning, and I'll see you in the next explainer.